at this point, we took a nice break that everyone really enjoyed. And when we came back from the break, we did a test of independence. So in test of independence, we're testing whether two multinomials are independent. More accurately, I'm going to write two categorical variables are independent. Okay. Might as well be accurate. So what we're going to do is we're going to do the same problem that we just did 13.8.1, but we're going to solve it as a test of independence, but we have a different question now. So the question isn't whether two groups are homogeneous, but rather is there a relationship between diabetics and your allele type. Now this is not good grammar, but that's okay, it's a stats class. So the picture here, I want to make sure you understand what independence means. So the setup is going to be that instead of dividing our population into in the previous example, two groups, diabetics and non-diabetics, and having everyone in each population indicate on their ticket whether they're what allele type they are, and then drawing from the groups separately. We're just going to pool all the people together into a single population, and everyone in the population has to fill out this 4-cell contingency table that basically indicates whether they're diabetic or not, and whether what allele type they are. Okay, so for every ticket, you can fill out this scatter diagram. So are you diabetic? Are you not diabetic? And what is your allele type? And so imagine that most people are the dominant allele type. So you get heavy capital B, and just light capital B, small b, little b, right? So if you had this, then I would say that the two categorical variables, diabetic, not diabetic, and allele type are independent. Compare that with this second scatter diagram. Here you can see that there is a correlation between whether you're diabetic or not and your blood type, your allele type here, right? So you see a positive trend here. So here these two random variables are correlated. We have a positive association, whereas in the previous picture they're uncorrelated. So now, how does this? How can you interpret this in terms of homogeneity? So we have two groups, diabetic, non-diabetic, in the previous example, and so you can see that the distribution. You can see that the distribution in this independent situation here, the distributions are the same, right? So you have heavy. For diabetics, you have heavy capital B, light BB and BB, and for non-diabetic, you have the same distribution, right? So these two distributions are the same. That's what I'm trying to say. Okay, that did not help, but anyway. So now we get down to it. So our null box now is going to be a contingency table across classification table here, where we take our two random variables, in this case allele type, which is our first categorical variable, crossing that with diabetic, non-diabetic, our second categorical variable, to give us this cross-classification table here. I'm going to indicate, so I is row, J is column. So so here I'm writing pi I equals 1. Pi I is 1. So this is the probability for I is 1 is allele type. And here pi j is 1, that is probability diabetic. That is awesome. So in this cross-classification, my assumption is that the first entry here, which I can shorthand write pi 1, 1, that's actually pi I equals 1 times pi j equals 1. So similarly here, pi 1, 2 is actually a product pi 1 times pi 2, and so on. So independence means that the probability that you're diabetic and your allele type is BB is equal to the probability that you're diabetic times the probability that you're BB, and so on. So that's what independence means in terms of probability, right? So we're drawing 104 from this now single population. We get our observed contingency table, and our null hypothesis is that pi ij is the product of pi I times pi j. In other words, we have independence for all i's and j's. And the alternative is that for some I and j, we don't get this product, right? So then comes the real fun, figuring out what the expected table is. And so for the first cell here, right, it should be, so the probability that you're in the first cell is pi 1, right? So this should be pi 1 times 104, because there's 104 draws. But the problem is we don't know what pi 1 for I and pi 1 for j is, right? So we have to approximate those. And to approximate those, so let's do that. So pi, so the MLE for pi I equals 1. So I equals 1, that is allele type BB or BB, right? And so here I can see that 16 out of 104 in my data were BB or BB, right? So this is 16 over 1 over 4, and our pi j equals 1 estimate, we see here that 51 out of 104 were diabetic, right? So we just take the product of those, right? And so similarly for all these other ones, and we get exactly the same expected table that we got for homogeneity. This is super fun. So now we can figure out the degrees of freedom. This is a bit different than before, although you get the same result. Here are null space. If you look at your null box here, notice that the marginal probabilities are just the probabilities for the various allele type and diabetic types that we have here. So if you just add the first column here, right, you're going to see that, right, pi I equals 1 plus pi I equals 2, they add up to 1. And we have the same pi j equals 1 in both cells here. So we're just, when we add them together, we're going to get the marginal pi j equals 1, and so on for the other examples, right? So this this contingency table here only depends on these four probabilities, and more generally, we would have j and I of these, of which j minus 1 and I minus 1 are independent. So we'd have a total of j minus 1 plus I minus 1 free parameters here. So that is the dimension. Whoa, that's the dimension for omega naught, and the dimension for capital omega is capital omega is just all of these cells are just probabilities that add up to 1, and they're not a product in this way. They're just probabilities that add up to 1, and whoa, and so we would have I times j minus 1 free parameters in that case. So that gives us the dimension of omega is ij minus 1, and so when you subtract these two, you get ij minus 1 minus I minus 1 plus j minus 1, which, do some fancy math, you can see that you're going to get I minus 1 times j minus 1. So then we can compute the chi-squared in just the same way, and you get exactly the same formula for your TS as before, and we reach exactly the same conclusion as before. The diabetics and allele type are dependent on one another. Awesome. So the assumptions that we have here, you can just read on your own, and I just want to compare and contrast these quickly. So we have one categorical. If you have one categorical variable, then you either have a goodness of fit test or a test of homogeneity. If you have two categorical variables, then you have test of independence. And really the difference between these is the way that the experiment is designed. And the best thing for you to do at this point is to actually practice to see what kind of problem, how you would set it up, and what kind of test you would use to answer the question. So I actually didn't have we ran out of time, and you are doing this in lab, but my endless sacrifice for you is evident here, because I have 3 more problems for you to do on this lovely Thursday. What I want you to do is read these, answer these 5 questions for each of these, and wow, I even provided you solutions. So you should be able to work through this and have a solid understanding of test of homogeneity and test of independence. Have a great weekend.